Learn like a pro.
Welcome. You know, when we think about what makes something strong, we usually think about the material itself. But it turns out the real secret is the invisible architecture inside. So today, we're going to explore the atomic principles that really define strength, resilience, and, well, even why things sometimes fail spectacularly. Okay, let's just jump right in with a classic engineering puzzle. Think about a furnace brick. This thing can sit in 2,000 degrees Celsius of heat, no problem. But if you drop it on the floor, it can shatter. So how can something be so incredibly tough, yet so fragile, all at the same time? The answer to that paradox isn't on the surface. It's locked deep inside, at the atomic level, and it all comes down to a single, powerful connection, the ionic bond. This is your briefing on that bond, because if you understand it, you'll understand why these materials work the way they do. To start, we have to zoom way in. We need to see how the fundamental building blocks of these structures are made. You can think of it as an atomic handshake, or maybe a bit more like a very deliberate business transaction. So let's be specific. An ionic bond is at its heart pure electrostatic attraction. You know the static cling that makes a balloon stick to a wall? It's that exact same force, just super strong and on an atomic scale. It all happens when one atom, usually a metal, gives away an electron, and another, a nonmetal, snags it. This transfer creates ions with opposite charges, and they become, well, irresistibly drawn to each other. Let's watch this transaction happen with a real example, magnesium fluoride. So you have a magnesium atom. It's got 2 electrons in its outer shell that it's just not that attached to. Then 2 fluorine atoms come along, and each one desperately needs just 1 electron to feel complete. A deal is made. Magnesium gives 1 electron to the first fluorine and the second electron to the other fluorine. And just like that, you get charged ions. The magnesium, having lost 2 negative electrons, is now a positive ion, Mg2+. And each fluorine, having gained a negative electron, becomes a negative ion, F-. And here's the really elegant part. The final compound is completely neutral. That single +2 charge from the magnesium ion is perfectly canceled out by the 2 -1 charges from the 2 fluoride ions. The books are balanced. The system is stable. It's perfect. Okay, so we've got our charged building blocks. But how do you get from a few ions to a super strong material? Well, they don't just pile up randomly. They assemble themselves into an incredibly organized and powerful structure, a true atomic fortress. What they form is called a giant ionic lattice. Now, this is not just a handful of molecules hanging out. We're talking about a massive 3-dimensional grid. Just picture a perfectly repeating pattern of positive and negative ions stretching out in every direction. Every positive ion is surrounded by negative ions, and every negative one is surrounded by positive ones. They are all locked tightly into place by those incredibly strong electrostatic forces. This rigid, interlocking architecture is the secret to the material's strength. So now we can connect that microscopic architecture to the properties we actually see and measure in the real world. It's time to put this structure through a performance review. Let's stress test it. This rigid lattice structure directly explains why these materials behave the way they do. First up, high melting points. It takes a ton of energy, a lot of heat, to break all those powerful bonds and get the ions moving. They're also really hard because those ions are locked in place and they fight against being pushed around. And what about solubility? Well, they generally won't dissolve in organic solvents, but they often do dissolve in water because water molecules can actually get in there, surround the individual ions, and pull the lattice apart. And this brings us right back to our furnace brick. Why is it brittle? Well, on the left, you see the happy, stable lattice. Positive next to negative, negative next to positive, all attracting each other, making the material strong. But if you hit it with a sharp force, you drop it, you can actually slide one layer of ions just one spot over. Now look at the right. All of a sudden, you've got positive ions lined up with positive ions, and negative with negative. Those powerful forces of attraction instantly become massive forces of repulsion. And the whole thing just shatters. That's why it's hard, but brittle. Okay, what about electricity? Well, for a current to flow, you need charged particles that can actually move. In a solid ionic compound, the ions are definitely charged, but they're locked into that lattice. They can't go anywhere. So solid ionic compounds are insulators. But if you melt it or dissolve it in water, you break that lattice apart. The ions are now free to roam. And because they're charged and mobile, they can carry a current, and the substance becomes a fantastic conductor. Now, understanding all this isn't just an academic exercise. It actually allows us to predict and even engineer the performance of materials. So, how could you make an ionic bond even stronger?
And here is the single most important design principle. The strength of that bond is directly tied to the size of the charges on the ions. The bigger the charge, the stronger the electrostatic pull. It's like upgrading from a small fridge magnet to a giant industrial electromagnet.
Let's look at a quick comparison. On one hand, you've got sodium chloride, regular table salt. It's made of ions with a +1 and a -1 charge. But now look at magnesium oxide. Here, the magnesium ion has a +2 charge and the oxygen has a -2 charge. We've simply doubled the charge on the ions, and as a result, the electrostatic force holding them together becomes dramatically stronger.
So, what does that stronger bond actually mean for performance? Well, the melting point of table salt is around 800 degrees Celsius, which is pretty hot. But the melting point of magnesium oxide, it's over 2,800 degrees Celsius. That's a 2,000-degree difference, just from doubling the ionic charge. This is the core principle behind high-performance ceramics and refractory materials. Charge matters. It matters a lot.
So let's bring this all home. What is the key takeaway here?
It's this. The atomic blueprint dictates everything. All those big, macroscopic properties, melting point, hardness, brittleness, they're all a direct consequence of that underlying giant ionic lattice. So the next time you see a material that's incredibly hard, can take insane amounts of heat, but shatters when you drop it, you now know the first question to ask. What does its internal architecture look like? Because that's where all the answers are.